All right, everybody. So thanks for tuning in and good morning or evening or afternoon. Welcome to today's edition of tinyML Talks. So first up, huge thanks to all of our tinyML Talks sponsors. So we have Deep Lite, Kickshow, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. So if you're interested in sponsoring the tinyML Talks series, please reach out to betty@tinyml.org for some information. So quick notification of our next tinyML Talks, which are going to be on Tuesday, October 13th. So we have Rajan Bhatt, who's the Director of Engineering for Machine Learning at Kickshow. And we have Chandrasekhar Vupalapati, who's the Senior VP of Products and Programs at Hanumayama Innovations and Technologies Incorporated. So every webcast starts at 8 a.m. Pacific time, same as today. And please reach out to us at talks@tinyml.org if you are interested in presenting. First of all, it's my pleasure to introduce Michael Gielda. So Michael Gielda is VP of Business Development and co-founder at Antmicro. He's also the Chair of Outreach at CHIPS Alliance and Vice Chair of Marketing at RISC-V International. So Michael, over to you.
Pleasure to be here. Thanks, Daniel, for the introduction. And today I'm going to tell you about running TF Lite on microcontrollers, which some of you might know if you're interested in tinyML, without hardware in Renode, which is an open source simulation framework that some of you might not know. So I'll try to tell you a little bit about it. And then how does it mesh with TF Lite Micro? First up, a little bit about us. My company Antmicro was founded 11 years ago. It's been a while. And I guess the one thing that's kept consistent throughout that period is that we help people build real products with open source. And this open source approach is, I think, the unique value that we add. We kind of work with workflows, design methodologies. We try to see how open source can transform various industries. And because of that, of course, we participate in various communities like Zephyr projects, like CHIPS Alliance, Open Power, and of course, RISC-V International. And work with a broad range of topics from defense security through mining, agriculture, robotics, aerospace, you name it. We focus mostly on the technologies, and we're very happy to apply them to various, mostly industrial use cases. And if you're interested in more about what we do, you can just take a look at our main page. There's a technology showcase. Like if you scroll down a little bit, it shows a bunch of tiles that lead you to various blog notes that describe various developments. The common point between those developments is typically that they're open source, and you can find most of them on GitHub, and you can use them as you want. So as I mentioned, we do a broad range of things from hardware through software and AI to FPGA and ASIC stuff. But I think what's important today is the tooling aspect. We develop tools and workflows to help with all the remaining aspects of our work. So while some of us are busy developing products, be it hardware or software based, many of us are also busy developing tools that help both us internally, that's where many of the developments originally come from, and other people that might want to work the same way we do. And of course, open source allows that. So it's a pretty neat solution. And yeah, the tools is the focus today. tinyML, most of you probably know that it brings a lot of new opportunities because you can have machine learning capabilities in smaller, lower power devices. And because of that, you've got less complexity, less communication. You can ensure higher standards of privacy. You can have less latency, and you can provide autonomy for various use cases. Some of these have been identified already. It might be gesture recognition, anomaly detection, some kind of voice-based analysis. But of course, many of those use cases probably lie ahead, and we don't even know yet what's going to be enabled by bringing ML to those really small microcontrollers. So it's a really exciting field. However, as exciting as it is, it comes with challenges. There's a lot of constraints in this field with power performance, of course, memory as well. And in general, I think one that I want to focus on today, testing is a huge issue, because if you've got those little devices, they don't necessarily offer a lot of debugging capabilities. They're not very, repeatable or deterministic in the way they run. This area has not been yet kind of really researched enough to provide good working methodologies. Of course, you can build your own little sensor or device, but scaling that up into a real system, configuring that in a complex environment, testing it properly, that's really hard. So that's kind of the challenge we're trying to solve. So this need for testing, of course, is not unknown to people developing TF Lite for microcontrollers. And as TF Lite kind of went into this world, the team behind it, led by Pete Warden, realized that, okay, we need to somehow improve our testing routine. And we're actually collaborating with them to make that happen with Renode, which is our open source simulation framework. And Renode kind of gives us the capability to build hardware-less flows that are based entirely on software. They're kind of CI driven, they're software oriented. We can also have full determinism. We can have various kind of plug and play options for peripheral models, which kind of enable new AI use cases. We can have reproducible development environments and build fairly complex setups, also with multi-node capabilities, which of course is not the current main focus, but at some point you might imagine if you build some kind of ML-enabled single sensor, the next step is to get it out to a system of multiple sensors working collaboratively. So those things are on our horizon. We're working with the team to enhance their workflow to use Renode. The collaboration is actually pretty long-term. We've started in 2018. And with Google, we've been doing a lot of work around open ASICs, open FPGAs. RISC-V is a big topic that we collaborate on a lot, but so is Zephyr, for example. We've been hard at work kind of making Zephyr more widely used both inside of Google and out. Actually, Google has recently joined the Zephyr project, which we're very happy about. And one of the topics that we collaborated around, of course, was enabling TF Lite to run on, first of all, RISC-V, on FPGA, that was our other focus area, and in Renode. We did this demo for soft RISC-V MCU on a very kind of cheap Digilent RT board. You can see a blog note around this on the TensorFlow Lite blog. Here's a link, and the blog notes just, kind of, I encourage you to read it. If you look at the, kind of scroll bar on the right, you can probably guess it's pretty long. Oh, sorry, that slide is wrong there. Okay, let's move to the demo. Basically, what you can see here is Renode running the software without any hardware whatsoever. So in the top left, you see the Renode log window. On the bottom left, it's the Renode main console. And on the right, you can see an execution where we're kind of telling apart different gestures. And it's all happening purely in software. This is all synthetic data that's being kind of recognized, and there you have an effect on your computer. Of course, this is an interactive run because it's easy to demo, but I'll tell you about kind of running this in CI and testing in a second. This is, of course, looping here. The repo itself, if you just go to this admittedly pretty long GitHub link, you'll see the kind of result of that work. And I'll try to walk you through it a little bit later. So yeah, what's this Renode thing I'm talking about? It's a framework, right? We kind of released it as an open source framework independently, so to say. It's its own brand. It is, of course, an Antmicro project, but it's kind of, it goes beyond Antmicro quite a lot these days. And it's actually been in progress since 2010, so it's quite, I would say, quite a long development. It started as a response to our internal needs, like many of the tools we build. We only open sourced it actually 5 years into the development process. We always had this idea that we would open source this, but I guess kind of becoming, kind of maturing to that moment where you actually have to go and push your baby online as an open source project sometimes takes longer than you'd like. And 2015 was that year, and since then we've gone through quite a number of iterations, so we're at version 1.10.1. Renode is an open source simulation framework, and it allows you to develop complex software for embedded and IoT systems. But that's kind of the primary use case that we saw for it when we first built it. But then people told us, hey, you could actually do architectural exploration and research on top of Renode. You could also kind of prototype silicon before it's there, or do some kind of hardware software co-development. That that wasn't the initial use case because we were focused on developing for platforms that already existed. But very quickly it turned out that the flexibility framework allowed additional use cases. In brief, how can we achieve those things? First up, we have plug and play building blocks. So it's very much about making things very modular and compatible with each other. We have a lot of APIs and interfaces that make you think about your boards as as a bunch of blocks that just interoperate, but none of them are really tied to a specific PCB design or whatnot. Then you also should think about it as a simulator, but not just a CPU simulator, right? Or not just even a system on chip simulator. It's also about peripherals and sensors and wired and wireless connections. So it operates on many levels. It's flexible, it's deterministic. It's also agnostic to the kind of software you want to run in it. So of course, today I'm talking about TF Lite on microcontrollers, but you can imagine running any other library on top of it. It's not tied to a specific firmware. It's very oriented to continuous integration and testing. And we try to also make it quite like batteries included, meaning that you can download Renode and you'll be able to run like 20 or something demos. Because we also serve binaries for those demos. We realized that, okay, if you have a simulator, you have to have some software to run on top of it. And very often people kind of downloaded Renode and said, okay, what do I do now? So we also provide those nicely packaged demos where you can just see Renode in action in 5 minutes. So yeah, as I mentioned, you can simulate a system on many levels, not just like CPU cores, but like right up to full devices and systems. So many people, of course, will want to simulate something like this, like an SoC with peripherals, and that's their main focus. They're developing, I don't know, an operating system, and that's the level of abstraction they'll be working on. But then there's going to be people who'll say, no, I want to develop some kind of ML-focused use case, right? And here I have a board with some sensors and buttons and stuff. I want to test this. And then there's going to be people who say, no, like the real important and useful context for me is this multi-node context where I can do connectivity as well. And we think that all of those user bases make sense. Like it's not that one of them necessarily kind of makes the other one obsolete. All of those levels need to be addressed. So we created a simulator that can kind of work on those different levels of abstraction. We've got quite a bunch of vendors that we support. Many of these are ARM-based platforms. They have been a major focus for a long time, Cortex-M specifically. And then since the advent of RISC-V, of course, we have really excellent support for RISC-V and a lot of platforms. There's a lot of RISC-V soft cores which don't even have logos that we can support here. So don't take this list as a full list, but more like just to give you a feeling of what kind of vendors we support. In terms of boards, there's quite a bunch. Some of them are, of course, supported by TF Lite Micro as well, hence the reason for today's talk. Some of them are not, and vice versa. Some of the TF Lite Micro boards are not yet in Renode. But in general, I'm showing 20 boards here. There's more, and there's different variants, of course, but I think everyone should find something they're interested in. So there's quite a lot of, Cortex-M boards, for example. There's some boards like the Solertia board, the red one here, with dual radio support. There's a really interesting, Polar Fire SoC development platform for anyone who's interested in RISC-V, or the Kendrite RISC-V platform, which is really small and cheap. There's the FOMU, which is the smallest FPGA board you can possibly think of, one that actually fits into your USB port. So believe it or not, but the picture here on the left, top left, is like not even life size. It's actually a zoom in of the board. So there's a real variety of different boards that you can work with in Renode. And to be really kind of precise about this, we care about peripherals. We want to support not just CPUs, but IOs, and that includes both like system on chip level IO, your SPICE, I2Cs, Ethernet, PCI Express, you name it, and also different kinds of sensors that you can connect to, for example, I2C or SPI, a thermometer, a humidity meter, accelerometer, and so on and so on. And of course, that in turn allows for the analysis of sensor data, so tinyML. We have integrations with a lot of frameworks. Here's a small list. It's not really complete, but definitely, as you can see, there's quite a lot of focus on testing and CI. I won't kind of dwell on details because there's still a lot of tinyML-oriented content I have later. If you're interested in kind of seeing something specific being done with Renode at work, there's a bunch of blog notes I can direct you to. There's the use with Verilator for hardware-software code development. There's an integration with Platform IO. There's, for example, a note from Memfold about integrating Renode with GitHub Actions for CI purposes. There's a lot of people using Renode for testing stacks and protocols like OPC UA or TSN. So really a lot of interesting use cases, and there's a growing number of blog notes and repos and places where you can find Renode at use, and many of those things we don't even know they're happening, or we're not behind. Like, we support them if we find them, but it doesn't necessarily mean that all of them were instigated by us directly. It's so cool to see our framework being used just everywhere. And of course, you can also run Linux in Renode. So like, here's the favorite use case of Drew, which is to see the tux in your frame buffer window. You can do that too. All right, so going forward to testing and metrics. This is the way we imagine Renode should be used. There's a local PC context that I mostly talked about before. You have your computer, you run Renode, you interactively debug your code, and perhaps test it every commit. But then you have this broader company environment, and there you have a server, more tests, you have colleagues that you're collaborating with, and you can do that very nicely and repeatedly. You can have reproducible work environments with Renode. This is very powerful in the company environment. We can attest that because we're using it internally, but so can our customers. So that's kind of how we want to enable collaboration, not just like a one-person workflow, but something that takes you beyond your desk. For example, for the demo I kind of mentioned before, the one that we did for Google, there's this Travis CI that can perform the entire demo procedure automatically. And if you want to see how Renode can work in this context, just go there and you'll be able to see that every commit gets tested, and then there's a Travis CI result. And this is really testing the machine learning algorithm there, right? It's really kind of doing an end-to-end test from compiling the source code up till actually running the binary and seeing the result and verifying that the result is proper. So if you take a look at that repo, I'll walk you through it because it's quite interesting. The files that we have here say quite a lot about how it go on and build something like this in Renode. The first file you see here is a C# file for a Renode peripheral. So in that original demo, we took an I2C peripheral and implemented that for the demo, but we did this internally in the demo, right? So you don't need to put stuff inside Renode. You can actually include it from outside. You can keep your code where it belongs if you need to. You can also, I think we encourage you to contribute things back into Renode. So actually, after a while, we actually took this peripheral and put it in mainline Renode so that this file is no longer needed here in this repo. But originally, we could quickly hack together something and put it in this repo, and we can also kind of include this file in runtime. Then there's data files. Like that's I think one of the most important aspects. You can actually have data files and replay them into a deterministic framework that's going to consume it and interpret it somehow and run it through your software and produce a deterministic result. So we have data for an angle movement and a circle movement, and we can detect it. Then we have a REPL file. We call it's a Renode platform file. All of our files extensions start with re, of course. So the REPL file is a human readable and modular format that's very extendable and enables you to create new platforms very easily. There's no coding involved. You just write something like this. So basically you tell Renode what's connected where at which address, which IRQs go where, and there you have it. You have your own platform. That might be like even a non-existent platform. Renode doesn't care. Your software might though. But REPL files actually enable you to build new variants of boards and variants of platforms very, very quickly. Then there's a REST file. This is just a Renode script file. So instead of running commands interactively, you can just script them in Renode. So it's like a Renode script. There's a robot file too. And robot is just a testing framework. So that's like a test in robot that describes the whole routine. Unfortunately, I don't have a slide for this, but I might add it to the slides later before they're published. Okay, so I kind of quickly run you through the whole thing. I think I've still taken up quite a lot of time, and we still have to keep some time for Q&A. So I'm going to walk you through a bunch of interesting developments that we have that I think will be really exciting, and many of them are actually already there, but they're fairly new. So I'm talking about them in the context of road ahead because I'm looking forward to building on top of them. First up, we actually kind of continue with the work to add those platforms that and demos that TF Lite cares about. This is, for example, an I2S demo for speech recognition that we recently added. And as I mentioned to you, we integrated TF Lite with Zephyr some time ago, which is great because we love Zephyr and we love TF Lite. And that enabled us to fairly quickly add a demo that's exercises another peripheral, I2S, and a microphone, and then of course you can process speech. And this shows how easy it becomes to add new things once you have a common platform for development, like Zephyr plus TF Lite. There's a blog note on our blog for this. I encourage you to read it. So as you can see, we're kind of continuing in the vein of implementing new platforms and demos as well. There's going to be quite a lot of work on adding some more platforms into Renode and then kind of getting that tested in TF Lite and so on. That I'm not going to talk about much, but there is ongoing work in that area. Then there's also quite a lot of exciting work around analyzing metrics. So basically we can take Renode and use it as a metrics analyzer framework because we're running the code, so we might as well analyze how it runs. So we can sum up the executed instruction count, memory accesses, peripheral access, exceptions. We can have virtual timestamps, we can have real timestamps as well. Virtual time in Renode, by the way, is deterministic. So if you run a test in Renode, since recently you'll actually get it to run a deterministic amount of virtual time. So you'll get the same result every time. And you can take this data that you extract from Renode, represent it as really interesting graphs, and you can learn a lot from how your software develops, whether you're kind of starting to use up more resources or less, and so on. This is quite powerful. And there's an MSc thesis from one of our students that kind of analyzed quantization as an optimization method. And he's been getting some interesting results, experimenting with different CNN model architectures. And of course, this is completely without instrumentation, right? We're not actually adding any debug code or like hardware tracing or stuff. It's all just the fact that we're running on a virtual runtime, which is our simulator. And it's very hard to get that kind of data from a real hardware in a consistent way. And Renode is also a very, very interesting tool for experimenting with various amounts of, for example, available memory. Like you don't know how your code's going to behave if you had twice the memory. Your board doesn't have that memory. It's just a board. You won't want to resolder parts just to check, right? In Renode, you change a number and you can take a look at how your software behaves. Another really cool development is this link, testing.renode.io. If you go there, you'll see a bunch of testing pipelines that we're kind of publishing results for. These are kind of CI tests, internal CI tests that we're running for various types of firmwares. Some of them are like RISC-V processors, some of them are ARM. There's different kinds of protocols like Ripple, UDP, TSN. There's quite a lot of different firmwares that we're running, and we're planning to enable quite a bunch more. So today we have a lot of those tests already created internally. We haven't published all of them yet, but we're going to, and of course that list will grow. So if you're interested in any of those firmwares or operating systems and so on, you should take a look. If you want to test Renode really quickly, there's this really cool way to do that using Google's Colab. If you don't know it, it's a Python-based workspace in the cloud. It's based on Jupyter notebooks, which you might probably know from other places. And it allows you to just run arbitrary stuff and share results and present things to people. The good thing is that you can just use one click to run everything because you get a dedicated server and your stuff runs there. So Renode, we just put Renode there. You can download a very simple package of Renode that kind of has all included. I'm using this little library I call pyrenode, which I subtitle a very bad lib to talk to Renode over Telnet. Planning to rewrite that to be much better, but it works, right? So why change it? And then you can take a look at that collab. We're creating quite a bunch more of those. We're really excited about this development because we can finally showcase to people in the cloud what kind of cool stuff you can do with Renode, and it's all just one click, no installation. For example, one of the things that one of our workers did here is a graph, an interactive graph of executed instructions using Plotly in Colab. And you should notice that one thing that we're pretty proud of is that those scripts that are to be found on GitHub are all generated from CI. They're written in a Git-friendly person format and just get converted to JSON automatically. Each instance that you're going to run is going to be a separate VM, so don't worry about like using up our resources or something. This is all Google's resources, so well, I mean, you can worry about Google. And then if you really want to run them locally, if you want to run Renode locally, you can still do that. There's a very quick and simple instruction how to do this. We do have interactive examples as well. So like you click a button and something happens in Renode. It's not trivial to get that, but you can do it. And yeah, if you take one of those collabs, you can actually edit it online and save a copy and just experiment, show stuff to people. We encourage you to do that. Yep, that's all from me. I hope I got you interested in this, and looking forward to the Q&A.
Thank you so much, Michael. It's really fascinating to hear about Renode, and we have some really good questions. So first of all, I think if you're in the audience, you should see a feedback poll pop up. So if you can take a couple of moments to give some feedback, but let's get started with asking some questions. So first of all, from Christian, is Renode a cycle accurate simulation?
Oh, sorry. The answer is no. This is an instruction set simulator. It's just a different class of simulators, right? It's meant for software development, and I guess that's the reason why we went with this mode of doing things. And the reason is, of course, you want to be able to like boot Linux very quickly or run your software many, many times. Having said that, we have concepts and the capability to introduce, interesting developments for, more fidelity than run-of-the-mill ISS would have. We've kind of done quite a lot of work in our simulation infrastructure to allow pretty fine-grained control of execution and stuff like that. Most of ISSs don't care about that. We do. So I would say we're pretty flexible and well-developed for an ISS. And certainly, if you care about specific things from the cycle accurate world that you'd like to model, we are doing work also in some research projects to enable certain use cases that would normally be handled with a cycle accurate simulator. But by default, it's an ISS.
All right, thank you, Michael. So second question, what about supporting a custom DSP core? How hard is it to define a specific core?
That depends on the core, right? It's not trivial because it's probably a different architecture that we might not support, but people have been looking at that, in various companies. I probably can't mention here, but there has been a lot of questions about, supporting various DSP architectures. And I guess it's not like years of work, most probably, but it's also not going to be done in a few days or weeks, right? It's somewhere there in between in that space.
Perfect, thank you. So next question from Jan. How deep does the simulation go? And can you do things like testing SimSysNN that depends on vector extensions on some Cortex-M MCUs?
Well, ARM is actually doing that, right? So ARM's using Renode for testing their stuff currently. So I guess the answer is yes. Now, how deep you can go depends on what Renode can support today. It doesn't do vector extensions for the CMSysNN, so obviously we'll need to implement that. But there's nothing stopping us. It's just a task to be done, right? We do have, for example, floating point support and so on. So it depends on the platform, really.
Perfect, thank you. Okay, next question. What goes into expanding Renode support to another chip or board? How does the hardware simulation work? So 2 questions there.
Okay, so depending on how close it's a very good question, because it shows one of the ways of thinking behind what we're doing. If your board is similar to other stuff that we already support, it's probably going to be fairly simple to add it to Renode, because we operate on this plug and play block-based approach where we've noticed that a lot of chips are just, a peripheral IPs being kind of purchased from vendors and reused a lot of the time, especially, for example, ST. Let's take a single vendor. They have a lot of, chips and boards. In reality, they are mostly rehashes of the same thing over and over and over again, which makes sense. They have different customers with different needs. So it's absolutely great. They have a big product portfolio. And for a layman, it might seem like, oh my God, how hard. It should be very hard to simulate that. But in reality, if someone tells us, hey, we want this STM board supported, most of the time it's probably going to be like some stuff we already have and some little things we have to add here and there. So it's going to be fairly trivial to add it. On the other hand, if you're targeting an architecture that we don't have, obviously it's going to be much more work. So it really depends on the platform, but we're trying to architect the framework so that there's very little code repetition, and as much as we can, we do, object-oriented inheritance, different versions of the same thing, typically end up not repeating the code that was already written. Because that's actually how people develop their chips, right? They reuse a lot of things. It's just very unclear to the general population what goes inside a chip and why does this particular ASIC have this kind of behavior and the next version doesn't. Because the ASIC world is not very open source. And as I might remember, we're also deeply involved in the ASIC development flows and opening up FPGAs and so on. So we have pretty good understanding of how the SOC development process works and why things happen like they do and why datasheets are closed very often and stuff like that. So Renode tries to organize this world a little bit. I think it does a pretty good job. I'm sure we could do a better job, but assuming that your thing is not super different than what we have today, then we try to make it as easy as possible to reuse what we have and just add what's missing.
Okay, thank you so much, Michael. So unfortunately, I think that's about how many questions we have time to answer, but there is a topic for this talk on the tinyML forum. So feel free to land there and ask some questions, and maybe Michael will be able to stop by and answer them. So, okay, so thanks again to our tinyML talk sponsors. So we have Deep Lite, Kickshow, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. So huge thanks. If you're interested in sponsoring tinyML talks, please contact Betty at tinyml.org. So here are some messages from our sponsors. So at Deep Lite use AI to make other AI faster, smaller, and more power efficient. At Edge Impulse, which is where I work and I'm the lead tinyML engineer, we've got a platform that lets all developers build tinyML models across multiple sensor types. So come check us out at edgeimpulse.com. Maxim Integrated enable edge intelligence across different sensors, different cores, and different types of AI. Kickshow AutoML for embedded AI provides an automated machine learning platform that builds tinyML solutions for the edge using sensor data. And Reality AI, which we've just seen from Stuart, is a tinyML for engineers tool for building products using tinyML. And finally, SynSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. So our next talks coming up from Rajan and Chandrasekhar are on Tuesday, October the 13th. So please tune in. It'll be same start time. And you can also contact talks@tinyml.org if you're interested in presenting at a future tinyML Talks session. So thank you so much for tuning in again today, and thank you so much to both of our speakers, and I'm looking forward to seeing you next time. Goodbye.